Hello. Today I'll be presenting you a paper on distributed logging or event logging, or you could think of it as system tracing. The core concept behind the paper is labeled as fault reconstruction principle, and the software they use is called Stitch. So let's begin. So where are we currently before this paper existed when it comes to distributed logging and distributed systems, and a way to gain insight into your deployment infrastructure? So distributed systems are systems with many machines launched on the network. They communicate on your infrastructure, they communicate over the network, and they have large deployments. And so a problem in one of the hosts or in one of the software instances or one of the processes can cause a cascading effect to affect other processes and other hosts on the system. So what is the first line of defense to combat this? Logging, right? This is something that's been around for a very long time, and is used, still today, and it basically involves sending log messages out to your system. And there have been processes in place to collate these log messages, things such as Splunk, and other types of log aggregation systems. Now, recently, there's been startups and other companies that have been looking into distributed tracing and how do you apply machine learning to, get a more rich insight into all these logs. So these systems have, typically a couple of downsides that this paper doesn't. And that is, for something like distributed tracing using Zipkin, it requires you to add your own instrumentation in your software. So your software developers will need to write software, like source code, in order to get these log messages to propagate and to work properly. And as a company or as a business owner, you would look for something that could work out of the box without the need to manually develop and add more to your current software. And so that's where this comes in. And then the other ones use machine learning to kind of build a richer system, but that's sometimes prone to brittleness. So what did the authors of this paper do? They provided, from a very high level, a 5-step approach. One, if we look at a log, which I believe is in my next slide, or this one over here, if we look at log messages, they're one line at a time, right? And they contain some information. So what we can do with that log message is we can try to extract what's labeled as object identifiers, which an object is literally just an abstraction. There's no intrinsic property about what an object is besides how it's defined. And then the next thing they do is, with all these object IDs, let's try to associate a type to the given ID. And then once you have a type, let's try to figure out how the types relate to each other, right? And it'll be interesting. I'll try to note this when I get to the point, but the semantics the authors use in this paper are actually the same semantics that have been used in relational databases to define object entity mapping or entity relationship mapping. And so it'll be kind of interesting to see that come up. And then the next step is we have the types, we have the object IDs. Let's correlate these objects together through an abstraction called an event. And so the events are kind of the glue which binds these objects together, what relates these objects together. And then the last step is, okay, we have this graph of, this big tendril graph of everything of our log system, but how do we make it something that's more user friendly? And so that's the identifying the execution structure. Okay, so briefly, that was the algorithm. What does this look like? So here's a brief snapshot of the user interface for Stitch, and there's a couple of key things. One is you can think of it as an object hierarchy, and you can see that when you have the user and the query ID to the application, and to these are the leaf nodes, and then it records events. So then we see with this object there's some events, which has tied these instances together, right? And time goes on, and you can see all the different events in which this object has appeared. Okay. So what exactly does it mean for these object IDs to be tied together, and for events to occur, for all what exactly are the definitions of some of these things? So events are basically the log message itself, and what is going on is if we can identify some object IDs in that log message, they belong to that event. And then what we can do is we can go, okay, but what are the types of these IDs? Well, if you look at the keywords and strings which are close to the ID, right? In the log message, you're not going to know what type, like the semantic meaning of that object ID's type is, but you can differentiate it from other types. Okay, and objects are correlated if they belong to the same log message. So we can see right here, we have two objects that are related to each other, related here, related here. And then an object subsumes another object if every time it occurs, the other object also occurs in the log message. Or sorry, if the object which is subsumed occurs in a log message, the parent object also is there. And then lastly, we can get to what I was talking about before about, what are the type relationships between these messages? And for those of us who've studied relational databases, we can see that they're actually the same relationships that are used to describe the entity relationship mapping. So, do these two types have no relationship to each other? Do they have a one-to-one relationship to each other? Do they have a 1-to-n relationship to each other? Or do they have an m-to-n, right, or a many-to-many relationship to each other? And then here, this is the slide that shows you the example log output. So the agent code for their system is pretty interesting. One of the things they do I'll get into it real quick. What this agent does is it scans the proc file system. So for those familiar with the Linux kernel, there's a sudo file system under proc, which contains current process data, which you can read using the standard libc system calls, or sorry, API. And so what they do is they scrape proc for the PIDs, and then also in proc contains information about the open file descriptors for those PIDs. And so with that, I can say, here's a given PID. Let me see what files this current process has open. And then with that, you can determine whether those files are log files or executables or class files, stuff like that. And with that, once you know the log files for that process, you can then start scraping that log file. So this is a zero configuration, right? No extra instrumentation needed for a way to start scraping log files off your system. Now, another thing they do, which is actually interesting, and it should be noted too, right? In their user case examples, they're using all Java-based systems, that they're Java executables. So this doesn't actually apply, but apparently this doesn't really apply for their user case examples, but apparently they put in an ELF parsing. They have an ELF parser, and they're able to actually, and I guess they'll probably even need an x86 parser too, to grab keywords from if you had a binary process running on your system. And then with those keywords, they're able to, through a dynamic programming algorithm, essentially find the parts of the log that are static components of the binary, and then figure out, okay, I know this is the static part of the log message. What's the dynamic part? And then once you know the dynamic part, you can then say, all right, these dynamic parts, these are my object IDs, right? And then the last part is once you have these object IDs and you build these regexes, given the static parts, the static strings, and the log messages, and you push it over the network to the server. The server is pretty simple. It has the output of the agent. It can give you the object IDs and their the events that they're associated with, but it doesn't build that nice intuitive graph that's rendered on the screen. And with that, there's also another dynamic programming algorithm which will reconstruct a much better looking graph. That's something that for those who are familiar with JSON would be like JSON objects, right? Where you can have this nice nested structure into these objects. And then it also does the UI rendering. Right. And then when it comes to results, so they had 5 use cases, and with some of the participants given the raw log files, the participants were not able, some of them were not able to find the problem in the software. So what this experiment was, right, is they came up with 5 use cases of software behaving with a problem. And they gave half the people, or they gave the control group, the raw log outputs, and they said, can you figure out the problem? And they gave the other people the stitch output, and they said, can you figure out the problem? And the people using stitch were able to figure out the problem more quickly, and accordingly, some of the people not using the raw log output were not able to figure it out at all. So if you're trying to judge, system monitoring, a system monitoring application by the amount of time it takes to figure out where the problem is, clearly Stitch is doing a good job. So, for the last parts, when I was looking at the results, there was some things that I didn't like what they were presenting in the paper, and so I'm not, clearly they're very good authors, very good researchers, but this is more just critiques for maybe people who want to discuss it more, or who want to put more thought into it. But the result in the results sections, they talk about the performance of their system, and the metrics they used was that it takes, for example, 3 hours to compute a graph for 24 hours worth of log messages. And that's great, but that doesn't tell us how many hosts that was, or how busy the servers were, or how many log messages were printed. And then, another thing they do is when they talk about these performance metrics, they talk about how the agent is CPU bound and how that's a good thing, which arguably it is in a lot of infrastructures where you have memory bound and IO bound and network bound systems, but it's not. CPU is still CPU. There's a context switch. Like, people do care about that. So it would have been nice to get, hard metrics into that. And then lastly, 4 out of their 5 use cases where they deployed their software were on Apache Foundation software, and most notably Hadoop software. So if I could pull it up real quick. Yeah. So they deploy it on applications such as MapReduce. That's part of the Hadoop infrastructure. They deploy it on Yarn. That's also part of the Hadoop infrastructure. And they deploy it on Spark. That's also part of the Hadoop infrastructure. And they deploy it on HDFS, which is also part of the Hadoop infrastructure. Those software applications all use the same logging format. And the algorithm they use to parse the object IDs from this log format is not what would be called reactive. It's more just a hard-coded implementation. And keep in mind, it's a very good implementation. It works very well. So that's not intrinsically a bad thing. But, if I was trying to evaluate would I trust this thing on my own infrastructure, I would want to see how this thing runs on a variety of different log formats. And they address that in the study. And they say that they tried it out on, different infrastructure, and that it didn't work well. And the reason, why they said it didn't work well was because it didn't follow the fault reconstruction principle, was that log messages need to contain enough information to reliably rebuild the system state at that time. So, that was one thing that I thought was a bit interesting. Overall, it's a very the software itself is very powerful, and having something like this where it requires no configuration, no code changes, it can automatically start aggregating the logs on your system with a low performance overhead. is quite powerful. So I think it did quite a good job there. And they're parsing the ELF binary and using proc to automatically find that is quite novel. So I think it's very interesting, and maybe can be extended in different ways to maybe use machine learning, or maybe a different way to parse that log structure to get something more complete. Anyways, that's it for me.